I think they're off one. They counted the midterm. Okay, let's get started. As most of you know, homework is due today. There'll be a new homework assignment will be posted probably tonight, and that'll be due in about a week or so. Any announcements from you all? Okay. Today I'm going to talk briefly about Spectra RF and Cadence. And if you haven't already done so, I encourage you guys to get familiar with Cadence and set it up and all that stuff. And I'll try to put up some tutorials and some pointers on the website to help you get started. Okay. Any questions? Okay, so let's go back and look where we left off last lecture. Now, we covered a lot of ground last lecture. Basically, we talked about mixers where we vary the transconductance of a device periodically. For instance, a mixer that maybe looks something like this, where we have an LO and an RF riding on top of each other, and the LO is a large signal, and the RF is a small signal, and the LO creates a time-varying transconductance. Okay, and that gives us a mixer. But then we also talked about another kind of mixer where we have a transconductor that essentially just takes an RF voltage and converts it into an RF current. And then, so this transconductance is constant. It's not a function of time. And then we create time variation using switches. So in this case, we have a current switching pair. So we could take our output here and drive this differentially with our LO. And basically on the positive LO cycle, we take our RF current, we dump it to supply. On the negative LO cycle, we take our current and we dump it to our load. And so effectively, the total transconductance is a constant times some switching function. And in this case, ideally, the switching function will be 1, 0, 1, 0. Okay? So these are two classes of mixers. This is a current switching mixer. And as you can imagine, there's also voltage switching mixers, which we'll talk about. And this is a, I don't know, for lack of a better name, let's call it a time-varying GM mixer. Okay. And so now you can dream up other ways of building a mixer. For instance, if I have a voltage-controlled resistor, right, and I vary its resistance periodically and run RF current through it, you get a mixer. So any time-varying circuit, periodic time-varying circuit, will act like a mixer. Okay. Is there a question?
Yeah, on the right side of the diagram, can you change the position of RF with LOs to the bottom tail?
Yeah, you can do that.
Large signal bottom.
Yeah. In which case, it won't be this kind of mixer, it'll be this class of mixer, right? Because then we're varying the bias current, which varies the GM. So let me just draw that circuit. So someone asked a similar question in office hours today. Is this a mixer? If I bring in my LO signal here, and my RF signal here. And indeed, this is a mixer because what you're doing is the GM of this device is now a function of time because the I is a function of time. Whoops. So there should be I of t over Vt. Well, last lecture we also talked about a dual gate mixer, and I think it's instructive to review why we can't switch the ports in a dual gate mixer, because this also came up in office hours today. So the mixer we talked about last lecture was we have an LO here and an RF signal here, As far as the RF signal goes, when the LO is positive, when the LO is not basically negative, when this device is in saturation, this is a regular cascode amplifier. But when the LO becomes sufficiently negative as to turn this device, basically move it into triode region, its GM drops and it creates a time varying GM. So this is also of the class GMT. On the other hand, if I switch things around, you can see that it's not a very good mixer. If I put in my RF here and my LO here, from the RF perspective, this is a very low gain amplifier because this is heavy amount of degeneration. And by changing the amount of LO, I do change the degeneration somewhat, right? But then I have to do something very drastic. So for instance, if I make my LO very negative, this transistor goes into cutoff, and then you present a certain amount of degeneration. You still have bad gain. When you turn this thing on, it turns into a current source, and you have another amount of degeneration, and so you still have bad gain. So this always has low gain. Okay. Also, to first order, if you look at this mixer here, you can see that because the gain is low for the LO port, there's a natural amount of LO rejection here, right? There is some capacitive feed-through as well, but overall, the LO signal is not amplified to the output like this circuit. So in this circuit, the LO port sees the full GM of this device to the output, and we rely on the filtering to reduce the LO leakage. Okay. Now, LO leakage, why is that bad? Well, usually the next stage after the mixer could be another amplifier, or it could be an A to D converter. And if you have a large LO swing going into that A to D converter, basically you could completely clip the next stage. It could overwhelm the signal because its strength could be a lot larger than the RF converted signal. So it's much better if we could get rid of that LO. Similar argument applies for RF. So we also last lecture discussed the concept of a single balanced mixer. And that was a mixer that basically was a differential version. We have our RF signal here. Again, we have our LO signal. And we take our output differentially. Okay? Now, because the output is taken differentially, again, the circuit operates just as before. We swing our current either to the left or to the right, depending on the magnitude of the LO. But because if we swing it left, this side is positive, this side goes negative. If we swing it right, the opposite happens. It looks like now we're multiplying our GM, our constant GM of this device, by an S of t, which goes between plus and minus 1. Okay? So S of t is unitless, and this is a regular GM. Okay? So the nice thing now is that because this G of t doesn't have any DC value, right? When we multiply our RF by this G of t, there is no RF at the output. The RF is rejected. For a symmetric LO drive. Okay. So as long as we can maintain this balance, we assume that this is a fully balanced circuit, we reject our RF. Okay. But we still have the LO leakage to the output. Okay. Let me also just kind of intuitively tell you guys something about the noise of this circuit. This is another discussion that came up in office hours today. Last time we talked about the noise in mixers in general, and we noted that one thing that makes the noise of mixers high is basically the noise at all the image frequencies folds into your IF band, and so you get a lot more noise than you would from a time invariant circuit. What's also interesting is if you go and basically plot the noise figure of, let's say, this mixer as a function of the LO, you'll find that the larger you make the LO, the lower the noise figure. Okay? And initially that might not be very intuitive, because you might think the larger the LO, the more harmonics I have, and so the more noise folding I would get, right? Which is true, but remember, as you increase the LO, you also get more conversion gain. So perhaps those two things could cancel out. There's another factor that comes into play that actually dominates, and that's the noise of this switching pair itself, right? The switching pair, this is not a noiseless differential pair. It has noise in it, right? So the equivalent circuit is as follows. Basically, there's a noise, V equivalent, in series with our LO. Now, the important observation to make is that if I swing this differential pair very hard, so for hard switching, the equivalent circuit is always something like this. The AC equivalent circuit from the RF port. That this V equivalent essentially looks like a cascode circuit, because this device is turned off by the hard switching action, or vice versa. And as we studied in LNAs, cascode configuration will reject the noise of this device, right? So the noise is rejected by 1 plus GM RO of the device. So the noise to the output is actually very low due to this device. On the other hand, if I do soft switching, then both devices are actually on, and it looks like a differential pair, which has gain to the output. Another way to look at it is, let's say that this device is turned on more than this device. Then this device now sees degeneration, which is this device in parallel with this device. And if this device is not off, the impedance looking into here is 1 over GM of this device. So then there's still gain from this device to the output, and vice versa. So for soft switching, the switching pair contribute to the noise. So that's why we like to have a very large LO swing, so that we minimize what we call the on time of both transistors. Okay? Question?
So in general, when you have two input ports like this, how do you characterize noise figure? You have two different noise figures for different inputs?
Well, the noise figure, the way we define it, so the definition of the noise figure is actually a little bit complicated. And there's two definitions for mixers. One is the IEEE definition, and one is kind of a microwave definition. And it's because of the fact that there's the image noise. So one way to define the noise figure, you might argue, is the same way. It's the SNR at the input divided by the SNR at the output, right? Where this is the input port, and this is the output port. Okay? The LO is not an input. So the LO, so it's kind of a black box, and the LO is kind of part of that black box. So this is the input, and this is the output. Now, the reason this noise figure definition is complicated is that a perfect multiplier, as you guys all know because you did the homework, has a noise figure of 3 dB, because the image noise folding back onto the same band. On the other hand, so because someone looked at this and said that's not fair, that means a perfect mixer already has a disadvantage of 3 dB. What if we assume that there's a filter, and that the filter actually rejects the image and the image noise? Then you would say the noise figure of an ideal mixer is 0 dB. There's also a complication, because you have to take into account if there's modulation in the image band. So there's a double sideband noise figure and a single sideband noise figure. Okay? Double sideband noise figure assumes that you have actual energy in both sidebands. So there's modulation in the image band, in which case If you go through even and perfect multiplier, you get noise from the image band, but you also get signal from the image band. So the noise figure again would be 0 dB. Single sideband noise figure, on the other hand, assumes that there's only information on one band and noise on the other. So single sideband noise figure is either a minimum of 0 dB with the IEEE definition, or 3 dB with the non-IEEE definition, let's say. And unless stated otherwise, you can assume that this is the noise figure. If someone says, what's the noise figure of a mixer, use this expression. In fact, that's what Cadence uses. So if you ask Cadence Spectre to calculate noise figure, it'll give you this number. Okay. Now, I didn't plan to spend too much time on noise of mixers. It's a rather advanced topic. A lot of good questions came up in office hours today, so I wanted to share that with you guys.
Question. So basically, you said that the thermal noise is constant all the way up to 1 terahertz or whatever. So basically, all the harmonics that you have there up to that point would contribute.
That's true.
So basically, depending on the number of harmonics you have up to that number.
But a perfect multiplier, right? That wouldn't apply for a perfect multiplier. But for any real mixer that's a time-varying circuit, you have to take that into account. Yeah.
So in this case, it's going to be humongous.
No, it'll probably be about 8 dB, 9 dB, depends. It's basically, if you think about it, so here's my LO. Here's my image bands around the first LO. Here's my image band around the second. So this is 2 LO. This is 3 LO, and so on. And they all fall into the same IF. So I'm going to sum up all these noise contributions. And if I do that, the gain from here is C1 squared. The gain from here is C2 squared. The gain from here is C3 squared, right? So the total power is Cn squared, sum of Cn squared, right? And by Parseval's theorem, we know that this is basically the energy of the signal. And so, depending on how much energy there is in the switching waveform, that's how much noise folding you get. Okay? And you can actually calculate what's the noise contribution from second compared to first, right? So if it's a square wave, the first contribution would be from the third harmonic, right? And that is down by a factor of 1/9. It's 1/3 squared. So you see the noise contribution is about 10%. And that's the biggest contribution. Then you add the fifth. That's down by a factor of 1/25. So this converges pretty quickly for most switching waveforms.
But you can't go below the noise floor, right? Below, at some point.
I'm sorry?
The different, as you get higher, if the coefficients get, extremely small, you can't get below 4 kT, right?
No, you can. This is the gain. They experience a gain, so the noise actually gets reduced. Yeah. Otherwise, you're right, the noise would be infinite if they didn't get reduced. Okay. Let's now talk about a double balanced mixer. And a double balanced mixer essentially is two differential pairs driven differentially. So it's a fully differential circuit. So this is the RF input. This is my, let me take the output single-endedly. And this is going to be plus LO. This is also going to be plus LO. And this port is going to be driven by minus LO. Okay. So this is also called a Gilbert cell. And the idea here is that it's going to work a lot like the single balanced mixer that we've already discussed. This is basically, let's just focus over here. So on the plus LO cycle, this transistor will be on, and my RF current will basically go from here to the output. And then for the negative LO cycle, this device will be on, and so the current from this guy will go to the supply. So from this guy's perspective, it looks like it's being multiplied by a square wave, just as before. But the interesting thing is that we have a second differential pair which is wired up with opposite polarity. So let me actually just draw what the circuit looks like for positive and negative LO. So let me just say a few things before we draw it. Let's say that this is a double balanced mixer. I already said that. That means it rejects LO and RF at IF. And I don't have to take the output differentially. And this is stuff that I'm stating, but I'll show you guys in a second. Okay? So let's see how this circuit works. So let's draw the signal for different RF. So let's go for a plus LO. So for a plus LO, the two outer transistors are on. And these devices are off. Okay. And this is our diff pair. Now notice this first diff pair, I've put emitter degeneration on there to linearize it. This first pair is just a GM stage, just like before. It's a differential GM stage. So this is the IF port here. This is the output. And this is the plus LO, and this is the plus LO. And this is the minus LO. Okay? So I'm assuming extremely hard switching. And so you could see that the differential current flows to the output with a certain value of gain. In the limit that this is very hard switched, all the current goes to the output, so the gain would be, let's say in this case, +1. Let me draw now also what happens during the negative LO cycle. Well, I guess I don't need to draw it. You guys can see what happens. So during the negative LO cycle, the current from this guy now is shunted to supply, but the current from here flows to this transistor and then flows to the output. So the interesting thing is that before, when we didn't have this transistor, the current would just get multiplied by 1 and then 0. Now the current gets multiplied by 1 and then -1 because this transistor feeds the output. So the gain, G of t, is again a constant GM times S of t, where S of t now goes +1, -1, +1, -1. Okay, does everybody see that? So maybe I could use colors. Now I think it's pretty clear. The important point is that I didn't need to take the output differentially. I could just take the output single-endedly, and I still get RF rejection. Okay? Now let's see how the LO is rejected. Okay? In the single balanced mixer, let's go back a few slides. This differential pair takes my LO drive and just gains it up to the output. It's not rejected at all. It's only rejected by the output filter. Okay? So the LO signal actually modulates the output. In a double balanced mixer, the LO has two paths. It has this path to the output and this path to the output. And these two paths are wired up in an opposite direction. So the gain from this path to the output is, let's say, GM1. The gain from this path to the output is minus GM1. So the LO perturbation, if these two paths are perfectly balanced, the current from here perfectly balances the current from here. So this current balances this current, and none of the LO current actually flows into the output. So this voltage will not move due to the LO voltage. So the LO is also rejected. Okay. Any questions about that? That makes sense? Yes, Debo.
So in single balanced mixer, we saw that when we took the output differentially, the gain was doubled because of the square wave. Here again, if we now take differentially, will it again be doubled?
Yeah.
So it will
Yeah.
be +2 -2?
Yeah, definitely. Well, it's not doubled, it's not +2 -2, because then the input is degenerated. It's a differential pair. So we get half the gain down here, right? And then to recover the gain, we could take it differentially output. So for comparing apples to apples, the gains are the same. Okay, so let's do a little bit of comparison. So the double balanced mixer has better linearity. That's because the signal now is being dropped across two transistors. So we can think of one half as processing half the signal and the other half processing the other half signal. That's because the signal is halved. The noise, on the other hand, is unfortunately doubled, actually quadrupled if we take into account the square. And that's because even though I can reject my LO signal, the noise on the LOs are not correlated. So because the noise of each transistor is independent from the noise of the other transistors, these signal currents cancel out, but the noise currents add in quadrature. And so the noise of these two stages adds to the output. So here it's even more important to have a very large swing to try to reject the noise coming from the LO port. Okay. Also, because this is fully differential, we can reject even order distortion, which is very important in a low IF or direct conversion receiver. Okay. Questions or comments? All right. So it turns out actually that the double balance and single balance mixers are probably the most common types of mixers out there. They're very, very useful cells, have a lot of good properties, and they're used almost universally. We'll talk about some other kinds of mixers that are becoming more popular a little bit later. Before I do that, though, I wanted to kind of take a little parentheses break and talk about a different topic. That's simulating mixers. And if you're using standard SPICE, you know that it's really difficult to simulate mixers. First of all, because mixers are time-varying circuits, you can't use AC analysis, right? So we cannot use AC analysis. That means you must use transient. To get the gain. Even just to get the gain of a circuit, you have to do a transient simulation. Then you have to do an FFT, right, after that. You have to follow it with an FFT to be able to discriminate the different frequencies at your output. The other thing that's a bummer is you can't get noise. You can't do a noise simulation directly. And when I say directly, the indirect method is a PhD thesis. And I'm actually serious. Somebody wrote their PhD thesis at Berkeley on simulating the noise in mixers using SPICE. Okay? So it's not something you want to do on a nice Sunday afternoon. Okay, so why is so we can't do noise, that's a problem. What's wrong with this transient? Let's also look at the transient. Let's take an example. Let me assume that my RF is at 1 gigahertz. I'm doing a down conversion to an IF of 1 megahertz. And my LO, of course, is RF plus or minus IF. So it's very close to RF. So now what we need to do is we need to resolve several frequencies at the output. We need to resolve the IF frequency, and let's say we want to also find our RF leakage and our LO leakage at the output. So let's say this is our LO, this is our RF, and this is our IF. So I need to resolve a frequency spacing delta F. Okay? And to do that, I need to run simulations on the order of 1 over delta F. Okay? Let me remind you of where that comes from. Okay? So the easiest way to see it is imagine you have just a sinusoid. And you want to take its FFT, right? You know that the ideal FFT would give you basically a spike, a delta function. But nobody has an infinite amount of time to run simulations, so what you do is you run a simulation that's t long, right? So I simulate up to time t. Okay. Now mathematically that's equivalent to taking your original sinusoid for all time and multiplying it by a window function that basically cuts off at time t, right? So this is the window function. Now, so that means that what you're really doing is you're taking the FFT of your window times your signal. Okay? And, of course, multiplication in time is convolution and frequency. And what's the FFT of a square window? What's the Fourier transform of a square rectangular function? Well, it's a sinc function, right? And the width of the sinc function is roughly 1 over t. So that means that when I convolve these, what I get is that. So how peaky this thing is depends on how long the simulation goes. And its shape depends on the window function I use. Now there's lots of window functions out there. You don't have to use a square window. You can use windows that have less energy at higher harmonics so you get a nice peakier response. But fundamentally, this relationship with t doesn't go away. You need to make a simulation time longer and longer to be able to resolve two close frequencies. Because let's say I have two frequencies that are closer than the sinc function, then when I convolve my sinc function, they're going to run into each other and produce a big fat pulse rather than two tiny narrow pulses, right? So that means that coming back here to our example, we need to run, let's say, at least a simulation that's 10 IF cycles, right? So for our example, I want a t simulation time of roughly 10 times the period of the IF. Okay? And that means that if I look at the number of RF cycles within the simulation time, this is inversely related to the frequency of the RF divided by the frequency of the IF. In this case, the RF is at 1,000 megahertz, the IF is at 1 megahertz, and that's 10,000 cycles. Okay, so that's a lot of cycles. Typically, when you run a simulation, you want to save at least 2 points per cycle, right? That's the Nyquist sampling rate. But let's say you're conservative and you save about 10 points per cycle. That means you have to save 100,000 points. that means you need to basically integrate 100,000 times, and in each integration point you have to run a Newton-Raphson iteration. So this is a very costly simulation. So even a simple circuit, you might find it takes hours to simulate. You guys are lucky, your computers are fast. 10 years ago you should have tried to do something like this. Okay. Now the same exact problem happened when we look at IM3, right? IM3 has the same exact problem. If you have two tones that are close together, the IM products are also going to be very close, and so the same kind of analysis applies. Okay. So this is why nobody likes to simulate mixers with transient. The preferable method is to use some either PSS technique, which is the periodic steady state analysis, and this is what Spectre does, or to use basically frequency domain analysis directly. And this is called harmonic balance. And this is what ADS does. Okay, so these are two popular simulation tools for RF and microwave simulation. Okay, so let's focus on PSS. So what does PSS do? So PSS tries to find the initial conditions that result in periodic steady state. Right? Takes a little while to get used to this. It's kind of backwards thinking. But the idea is that my circuit, let's say I excite it with a periodic input. Initially there's going to be a transient response, right? So I have a periodic input. Then I get a transient response, and it dies off. And then finally I get my periodic response, what we call the forced response, which is at the same frequency as the input, or its harmonics, right? So the idea of PSS is, instead of running a long transient to get to this state, what if I could find the initial conditions in steady state? Then all I have to do is simulate one cycle, and I know the complete behavior of my system because it's periodic. So the trick is to find those initial conditions. So a PSS iteration, so a PSS simulation finds the periodic steady state and usually about 4 to 5 iterations. And the way it does this is it does, in each iteration, it simulates about T naught, basically. So it only simulates roughly one cycle of the circuit. So within 4 or 5 iterations of simulating one cycle, it finds a periodic steady state. Now that's really powerful, right? So if we could use this information, we only need to do about 4 or 5 iterations, 4 or 5 periods, as opposed to, like, let's say 10,000 periods that we talked about before. The reason it can do this is, let's say PAC. Actually, before I get to PAC, let me just say a couple of things here. So there's a couple of conditions for PSS to converge. So the circuit cannot be chaotic. Okay? That means that it can't, basically, if I put in a periodic input, the output has to be periodic. It can't just wander off in chaos. Okay? And then the other thing that you need to know when you run PSS, what parameters do you give it? First, you have to tell it, is this circuit a driven circuit or an autonomous circuit? Okay? Autonomous circuit is something like an oscillator. For now, we're talking about mixers, they're driven circuits. Okay? So we'll talk about autonomous circuits later. The next thing we need to give, so we have to do this checkbox. The next thing we have to check off is the large signals in circuit. Okay, so for a mixer, what are the large signals in a circuit? The LO port. There are situations where you want to put in 2 tones or 3 large tones. Then you need to put in basically you could also put in other large tones. For instance, as we'll see, if you want to do a true IM3 simulation in a mixer, you would actually need to specify at least 2 large tones. Turns out that with small tones you can get away with it, but we'll come back to that. Finally, you need to give the beat frequency. So for instance, if you have 2 large tones, it would just be F1 minus F2, right? But actually Spectre can calculate what the beat frequency is automatically if you give it more tones. Finally, you could give it a parameter called T-stab or T-stabilization. This is additional time to run simulation beyond period. And this is useful for oscillators. It's not really that useful for mixers, so you can more or less ignore it. Okay. So any questions up to here on what periodic steady state analysis is? So let me just repeat. We haven't said anything about mixers. All we've said is periodic steady state analysis tries to find the steady state periodic solution. Okay? And if you think about normal SPICE, there's no way to do that unless you simulate it for a long time. Now some circuits get to periodic steady state very quickly, okay? Because, for instance, let's say I have just R's and C's in my circuit, it's critically damped. A few cycles, boom, the transients died off, right? Let's say I have lots of poles in the left half plane, and they all have very short decay times, so they all decay away, and I get to periodic steady state. Other circuits, though, let's say high Q circuits, take a long time to reach periodic steady state. So let's look at a high Q circuit. So let's say I have an amplifier and the output has a high Q tank. And let's say it's really large. Let's say it's 10,000. Okay? For instance, this might be a crystal at the output. If I put in a sinusoid F0 close to this frequency, then I'm going to basically have to wait until the natural response of this crystal dies off. So if I basically just turn the circuit on, it'll start ringing like a bell. And this ringing can go on and on and on, and it goes on for 10,000 cycles, right? So if I'm doing a transient, I'd have to wait 10,000 cycles, roughly, until the transient dies off. On the other hand, if I could find the final charge on this capacitor and current in this inductor, and also the same inside here, all the voltages across the capacitors in here, that result in periodic steady state, I could just apply those voltages and boom, the circuit would be in periodic steady state. It wouldn't ring at all. So that's the idea behind PSS. Okay, any questions? That makes sense? Okay, I think I have a question back here.
So what if you have multiple tones in your system and they're not integer multipliers of the other frequency? What's the periodic?
Well, you still get the beat frequency, right?
No, 1's 3 megahertz, 5 megahertz.
Yeah, it's not. It basically never goes into true periodic steady state. It goes into quasi-periodic steady state. And there is another analysis inside Spectre to handle those kinds of circuits. Okay, good, very good question.
Before the circuit gets into steady state, we're not interested in the behavior before?
That's also a good question. We may be, in which case we have to run transient. But a lot of times we're interested in the steady state. For instance, you turn on your radio. You don't care what happens the first 1 microsecond, right? You care about the steady state once the radio is working. So that first 1 microsecond is actually dead time. We wish we could make it shorter, but sometimes you can't. Okay? Okay, so let's talk about periodic AC analysis, or PAC. So PAC is just like doing AC analysis, but instead of doing AC analysis about the DC operating point, it's AC analysis about a periodic operating point. So this is the circuit is linearized around a periodic operating point. So compare it to regular AC. In AC, the circuit is linearized around a DC operating point. Okay? Now, what's complicated about PAC is that there's, what does a transfer function mean, right? In fact, you can see that in periodic AC there are as many transfer functions as there are harmonics in your signal, right? Again, simple mixer is a great example to see that. Here's my LO, here's my 2LO, my 3LO. Okay? And for instance, let's say I apply a signal at IF, and it's an upconversion mixer. Well, I know that this can mix to these sidebands, it can mix to these sidebands, it can mix to these sidebands. So which transfer function should we look at? And how many transfer functions are there? There are as many transfer functions as there are harmonics in the strong tone. Right? And that might be the LO in the case of a mixer. Okay. Kevin, it looks like you have a question forming in your mind.
What does it mean for a transfer function when it's not linear?
It means output over input, right? And that's the problem. It is linear, but it's time varying, right? This is a linear analysis. That's why it's called AC. Okay, so what we need to do is specify a reference. Basically, we have to specify which transfer function we care about. So the input frequency, let's call that Fi, is translated to frequencies F input plus K F naught, where F naught is the beat frequency, which in a mixer is just the LO frequency. So for instance, the K is equal to 0 sideband. That should be the same as, that's the DC component of the LO. So this is the time invariant behavior. Okay. K is equal to -1. That's frequency down conversion. Okay. K is equal to +1 is a normal up conversion. And so on. So K minus 2 is second harmonic mixing. And so when we do our PAC analysis, we have to tell it which sideband we care about. Okay? And then that's it. It's just like doing regular AC analysis. You supply your input frequency and the sideband, and then you plot the output frequency. So there's one interesting thing is you specify the input frequency as either an absolute frequency or a relative frequency, where you'd specify it relative to the beat frequency. So I could say 100 kilohertz away from the beat frequency, or a megahertz away from the beat frequency. Or I could say it's 1.1 gigahertz explicitly, for instance. Okay? Questions about PAC? Now here's what I suggest you guys do is, the first time you run PAC, run a very simple circuit that you've analyzed by hand, let's say a simple switching mixer, and you know all the right answers. You know exactly what the conversion gain should be to the first harmonic, to the second harmonic, and so on. And check it to make sure you're running it correctly. There's also some good examples that come with Spectre that you can try out. Okay. Pretty clear? Yes?
So PAC is a subset of PSS? Or?
Yeah. You have to first run PSS. So when you run AC analysis, you first have to run DC analysis, right? You need to find the DC operating point. So first you run PSS, and then you run PAC. So you can't just run PAC without running PSS. It's a good point. Okay. Well, just like there is PAC, there's also P-noise. So P-noise does exactly what we want. Because it linearizes about the periodic operating point, it can calculate noise transfer function. So draw this figure again. So in P-noise, I specify my output frequency. And let's say this is my beat spectrum. Then it knows that the noise folds. It knows what the noise spectrum looks like. Let's say it's flat like I've shown here. And it can calculate all the noise folding as before. So P-noise takes noise folding into account. And in order to make it work correctly, you have to specify again the sideband. For instance, K -1 for a down conversion mixer. And you have to specify the number of harmonics. I think it calls it is it the maximum number of sidebands or the number of harmonics? Maximum number of sidebands? Yeah. So you also have to specify the maximum number of sidebands. Because obviously it can't do an infinite number. It take an infinite amount of time. So what it does is it says, you tell it, take 50 sidebands into consideration, right? Usually that's pretty good. But depending, and the more sidebands you specify, the longer it takes to do the noise calculation. But you basically pick enough sidebands until the answer doesn't change, right? So if you're really interested to know how much noise folding is going on, you could start out and say, just include the noise from the first sideband. Then you could say, now add the second sideband and the third sideband, and you'll see the noise figure go up step by step. Okay, questions about PAC, P-noise? So just like PAC, you first have to run your PSS simulation before you can run your P-noise simulation. Yes?
Do you also need to specify the bandwidth over which noise is integrated over? Because bands all have P's in the equation.
Yeah, it's a good question. You can tell it if you want integrated noise or spot noise. And you have to also tell it where your input and output port are. So it's a lot like just doing regular noise analysis in that way. It also gives you a nice noise summary, so it'll tell you where all the different noise sources, what their contribution is to the total output noise. Okay, so that's the first detour. The second detour is I want to talk a little bit about transformers. Okay. So transformers. So before we talk about transformers, let's look at coupled inductors. So I have two inductors, L1, L2, and I define a mutual inductance between them. And let's call this I1, I2, this V1, this V2. And I know that these two inductors satisfy the following equations. that the voltage across V1 is j omega L1 I1 plus the mutual inductance j omega M I2. And by symmetry, the same thing applies to V2. And the mutual inductance is sometimes specified with a K value. This is the coupling factor. And you can prove that K can't be larger than 1. This can be proven with conservation of energy. Okay. And you probably saw this in physics or in 117. Okay. Now, the way that inductors actually work, one way to look at them is through the concept of flux. So just like, so flux plays the analogous role as charge does in electrostatics. In magnetostatics, if you have a current, it generates a flux, and basically, if I change the current, that changes the flux, and changing the flux gives us a voltage. Okay? So if you think about this relationship, right, because the duality between inductors and capacitors, we get this relationship. Okay. Now, so physical, the way this works is, for instance, I can have, let's call this L1, and this L2, V1, V2. We can see that if I pass a current I1 through this, it will generate some magnetic flux, and some of that flux will cross into the circuit 2. And that flux, if it changes, generates a voltage on port 2. So this is the physical mechanism for how coupled inductors work. If all the flux from one circuit enters the flux of the other circuit, then the K factor approaches 1. If the flux actually intersects another circuit with the opposite orientation, as I've shown here, this circuit is wound in one direction, this one is wound in the other direction, then a positive flux here corresponds to a negative flux in this circuit. And that could make my mutual inductance negative. Or if you like, you can make K negative. You can either absorb that into K or into M. So I can also induce negative voltages. So I can easily flip voltages around using transformers, using coupled inductors. Okay. Questions? Okay, hopefully this is all a review. Let's also review ideal transformers. So ideal transformer, the way we draw it is we put these two bars next to these two inductors. And basically the relationship for an ideal transformer is that we get some voltage scaling and some current scaling. By conservation of energy, I just need to tell you that there's just voltage scaling, and automatically the current scaling has to look like this. That's because this is a passive device. So it cannot, it's a passive lossless device. So it cannot store, it can't dissipate energy and it can't supply energy. So V1 I1 plus V2 I2 has to equal to 0. Okay. Now, it turns out that if you ever try to build a transformer, instead of getting something like this, you get this. This is Lx, this is Ly. And then inside here, you get yourself your nice ideal transformer. Let's say n to 1. But you always end up with these extra inductors. And so what I'd like to show you guys is that this circuit here is equivalent to two coupled inductors. That's because anytime we build a real transformer, it's actually built up of coupled inductors. So I need to show you that this is actually equivalent to this. Okay, is that clear? So let's see how that is equivalent. So let's take V1 over here and V2 over here. Now, just using this circuit, V1 is j omega Lx I1 plus, so this is I1 flowing into here. This is I2 over N, where this is I2. I1 plus I2 over N times j omega Ly. Okay? And if I basically group terms, this is Lx plus Ly I1 plus j omega Ly over N I2. Okay? And then if I take the voltage at the secondary, well, the voltage at the secondary is just Vy divided by N by this perfect transformer action. And Vy is simply I1 plus I2 over N times j omega Ly, and then I divide by N. So I could write that as I1 times j omega Ly over N plus I2 j omega Ly divided by N squared. Okay? So this is, let's call this equation 1 and this equation 2. You see these two equations actually look a lot like two coupled inductors. This is j omega L1, this is j omega M, this is j omega M, this is j omega L2. Right? So I could say that L1 is Lx plus Ly, L2 is Ly N squared, and M is Ly over N. Okay? And so I could solve these three equations, and you'll find that N for the ideal transformer is K square root of L1 over L2. Ly is K squared L1, and Lx is 1 minus K squared L1. Okay? So let me label that on the transformer. So the claim is that if I have two coupled inductors, I've shown you guys that this is equivalent to a circuit like this. Ideal transformer, DC isolation, N to 1. This is 1 minus K squared L1. This is K squared L1. And there's nothing magic about putting this on this side. I could also move these inductors to this side, right, by symmetry. Okay, so now we claimed that a very good, we say that two inductors are tightly coupled. K is almost 1. K approaches 1. So in this equivalent circuit, if K approaches 1, this inductor goes to 0, but I still end up with this inductor. So no matter how hard I try, the best I can do is this. This is the best transformer I can build. And this transformer, this non-ideal transformer, tells us that you can't ever pass DC current through a transformer, right? If I pass a DC current in here, what happens? It just gets shorted to ground, right? So any real transformer will only work at AC frequency. Now what's interesting about an ideal transformer is that it'll even work at 0.00001 hertz, right? hey, that's an AC signal, it'll work. But no, in reality, there's a cutoff frequency. There's winding resistance, and so you get a cutoff frequency. And so you can show that there's actually a transition frequency. You have to be above that transition frequency for this to work. So to push the transition frequency lower and lower, I have to make this L bigger and bigger. And that's why low frequency transformers are huge. They're physically very large to get very large inductance. They also use magnetic cores to boost the inductance. And so most of you guys were probably born after the days of transformers. Now everything is a switching power supply, right? So how many of you guys have ever lifted a real transformer? Okay, you guys aren't as young as I thought. Well, no, it's the grad students. Yeah, so the undergrads have probably never lifted a real transformer. You know, imagine lugging around one of these transformers in your suitcase for your laptop. The other problem with transformers, of course, is that the voltage is fixed. So if I'm on a 120 line, I have to use a different transformer than a 220 line. So if you traveled with a transformer, you needed to carry around 2 transformers with you. Nowadays, of course, we use switching power supplies, and so we don't have to worry about that. But that explains why the transformers were bulky, they're big, and they had the magnetic core, which made them heavy. So let's look at how you would build a high-frequency transformer. Actually, before I go there, let me just say, at high frequency, this approximately approaches an ideal transformer, because this is an open at high frequencies, right? If this is large. So to make the transformer work, I need to make the winding inductance large enough. Okay? So let me compare a low-frequency transformer and a high-frequency transformer. So I'm going to use a magnetic core, and I'm just going to wind my primary here and my secondary here. Now at low frequencies, this core is very nice because all the magnetic flux from this winding goes inside this core and reaches V2. Okay? Unfortunately, at high frequencies, let's say above 100 megahertz, the core doesn't work. Okay? So it's very hard to find magnetic materials that work at high frequencies. So at high frequencies, this core is essentially not there. So if I build a transformer like this, so here at low frequencies, K is roughly 1, and L is huge because of the core. The L is boosted by basically by the magnetic K factor, right? The magnetic permeability, mu. Whereas at high frequency, this thing just looks like air. It doesn't do anything. So mu is mu naught. So if I had a mu of 1,000, now I have a mu of 1. And if I build inductors like this, basically I'll get coupling factor that's way too low. Let's say 0.01 or something. Okay, I don't feel like drawing this again, so I'll be lazy. Okay, so bad idea. So the way that people build high-frequency transformers is actually they take 2 wires that are insulated and they twist them together and they wind them around this core. Okay, so let's see how we draw this as painlessly as possible. Let's say I'll just draw this like this, and hopefully you guys will know what I'm talking about. So this is actually plus minus. So this is the primary of 1. This is the primary of 2. Okay. So what I've done is I've taken 2 wires and just twisted them together and formed a transformer that way. Okay. So really this is port 1, this is port 2. So I need to bend this to bring these 2 leads close together, right? So that's why I actually would bend them together produce a transformer like that. So you might ask, why use this core, right? It's not doing anything for you. Well, it turns out that the core is useful because it can reject common mode signals. Let me explain that very briefly. So if I send in a differential signal, that means that current 1 and current 2 are out of phase, then the actual magnetic flux produced by this circuit is very small because these are twisted together, very close together, and the flux area is very small. And so that means that differential signals put in very small amount of, generate very small amount of flux. Common mode signals, on the other hand, actually for a common mode signal, I put the same current through these two wires. So it just looks like one wire wound around here like this, and that would generate a lot of magnetic field. So a common mode signal would generate flux in the core. And it turns out that these things don't work because they actually produce loss at high frequency. So because of the lagging, because the magnetic moments, the magnetic domains lag the signal, they actually look like a loss term. So they make our mu imaginary. So for a differential signal, because there's very little magnetization, there's very little loss. But for a common mode signal, there's lots of magnetization and therefore lots of loss. So this structure naturally rejects common mode signals. And later on, we'll see why we want to reject common mode signals. Okay, so we've covered a lot of ground. I'm going to stop and see if you guys have any questions before we go on. Yes?
So in CMOS technology, how do you build the core? From which material?
You don't. Yeah, in CMOS technology, so these are basically off-chip transformers, right? The way you build transformers on chip is very differently. First of all, they're air core inductors. They actually use silicon or silicon dioxide, but these are non-magnetic materials, so effectively they're air core materials. And so the way you build an inductor on chip would be you would just use a spiral inductor like this, right? So this is an inductor. One way to build a transformer is very much like this. I just wind a secondary around it. So this is a transformer. Or I could do something more symmetric. If I want L1 and L2 to be the same, I could, let me draw it like this, yeah. And then I can make L2 come from here. So this would be a more symmetric structure. Or I could do a structure like this. So this is a symmetric winding. I can do another winding that effectively does the same thing. A little bit hard to see, and I actually mucked it up. So anyhow, you could build a symmetric version of these transformers. But these are planar structures on chip. They have to be planar for the most part. If you have multiple metal layers, you can actually build non-planar inductors and transformers. We could talk about that more, but it's a little bit off course. So let's get back on course. Okay, any other questions? Yes?
So in the twisted pair example, and even here, how do you make a transformer with turns ratio not equals 1 to 1?
That's a good point. Generally, it's harder to do that. You can't do very large ratios. What you do is you put turns in parallel. So let me show you how you would do that on chip, and then you'll get an idea. So let me say I do something like this for my primary, so it has 3 turns. And then for my secondary, there's a different colored pen. I have 1 turn here, right? So this is just 1 turn. So this is a 3 to 1. But I might as well put another turn in parallel. to lower the resistance, and maybe even a third turn. So this is like a 3-to-1 transformer.
Differential flux still cancels, still
No, you
positive?
don't get that benefit. A 1-to-1 will only give you that benefit. Okay. Well, one of the problems with these transformers is capacitive coupling. Because I had to move these wires so close together to get good magnetic coupling, I'm going to get good now capacitive coupling, right? And capacitive coupling has the wrong phase. It actually cancels out the magnetic coupling, and it destroys basically it destroys the structure. Even for an off-chip structure like a coil, ultimately the self-resonance frequency is limited by turn-to-turn capacitance like this. At really low frequencies, this capacitance doesn't do anything because this is all shorted. But at high frequency, these turns, you can think of these turns as being basically loop inductors which are coupled together. And there's capacitance going like that. So at really high frequency, the potential, let's say from here to here, is different, and so current can flow in these capacitors. So ultimately, all inductors self-resonate. Okay? Now for off-chip kinds of inductors, it's usually the winding inductance that dominates. For on-chip structures, there's a huge capacitance to ground through the substrate. Similar thing here. And so this will ultimately lead to self-resonance in the structure. Okay? So the problem with transformers is that, one, they tend to be big, and two, self-resonate at relatively low frequencies. So off-chip, you can use, if you have micro-machining technology, you can build transformers up to a few gigahertz. If you don't have micro-machining technology, up to a few hundred megahertz. You can hand-wind good transformers up to a few hundred megahertz. On chip, you can build things actually up to very high frequencies because you can make things so small. But then the amount of inductance you get is limited. So ultimately, you end up with tuned transformers. So a tuned transformer would have this ideal transformer, and then it would have k squared L1, where unfortunately k squared L1 is not a large enough impedance that we can neglect it, so we have to put a capacitance across it to tune it out. Okay? So that means that our circuit is now a tuned circuit. And so it has a passband just like it would an LC circuit would. Okay? Questions about transformers, Firas?
Transformers, but about mixers, I mean, up to what frequency you can use the mixers that we have demonstrated?
That's actually a really good question. Nobody has derived a nice, beautiful equation that says if the FT of the transistor is this is the highest frequency you can use the mixer. Most of it is kind of intuition. You build mixers, you have experience with them. But certainly, most mixers would operate about FT over 5, FT over 4. That would be kind of a loose limit. Your gain starts dropping considerably, conversion gain, if you go higher than that. I mean, you're limited by how fast you can switch transistors and the actual GM of the transistor. So we know the GM starts to drop after, right? The GM of the transistor starts going like FT over F. So if we get closer and closer to FT, we have less and less GM. Then our ability to switch transistors gets worse and worse because of that huge capacitance on these devices. So there isn't a clean answer I can give you. I can tell you, though, if you want to go to really high frequencies like terahertz, you use diodes. And so next lecture we'll look at diode-based mixers. Okay. Any other questions? All right. See you next week.